Welcome to Lesson 12. Last time we learned about impulse response and convolution. Today we study the step response, one of the most important tools for analyzing system behavior. We will compute step responses for the integrator, the first order lag, and the time delay. The Heaviside step function, sigma of t, is 0 for negative time and 1 for positive time. It represents switching on a constant input at time 0. Its Laplace transform is 1 over s. The step response of a system is the output when this function is applied as input. To compute the step response, we set u of s equal to 1 over s. Then y of s equals g of s times 1 over s. To get y of t, we take the inverse Laplace transform of g of s divided by s. This is the standard procedure for any transfer function. The simplest example is the pure integrator with g of s equals 1 over s. The step response becomes y of s equals 1 over s squared. Taking the inverse Laplace transform, we get y of t equals t times sigma of t, which is a ramp. The integrator accumulates the constant input, so the output grows linearly with time. Next, we study the first order lag. Its differential equation is t times y dot plus y equals k times u. Here, t is the time constant and k is the proportional gain. Taking the Laplace transform with zero initial conditions, the transfer function becomes g of s equals k over 1 plus st. To find the step response, we compute y of s equals k over 1 plus st times 1 over s. Using partial fraction decomposition, we get y of t equals k times sigma of t times 1 minus e to the minus t over t. The output starts at 0 and exponentially approaches the final value k. Let us see how the time constant t affects the response. For small t like 0.5, the system responds quickly and reaches steady state fast. For larger t like 3 or 10, the response is slower. In all cases, the output reaches 63% of the final value at time t equals t. This is a key property of first-order systems. What happens when the time constant t is negative? The transfer function still looks the same, k over 1 plus st, but now the pole is in the right half of the s-plane. The response diverges to infinity instead of settling. A negative time constant means the system is unstable. Stability requires t greater than 0. The time delay is a special transfer block. The output equals the input shifted by delta time units, so y of t equals u of t minus delta. The transfer function is g of s equals e to the minus delta s. Applying a step input, the step response is simply a delayed step that jumps from 0 to 1 at time t equals delta. Let us summarize the four standardized transfer blocks. Proportional gain k, with step response k sigma of t. The integrator k over s, with step response k t sigma of t. A ramp. The first order lag k over 1 plus st with step response k times 1 minus e to the minus t over t, and the time delay e to the minus delta s with step response sigma of t minus delta. These are the building blocks for modeling any linear system. Excellent work. In this lesson, we learned that the step response is computed by multiplying g of s with 1 over s and taking the inverse Laplace transform. The integrator gives a ramp. The first order lag gives an exponential rise toward k, with time constant t determining the speed. A negative t means instability, and the time delay simply shifts the step by delta. Next, we will study second-order step responses.